Let us now consider capacitors in parallel. If we force a constant DC current through capacitors in parallel, the current will split up, and only a fraction of the total current will flow through each capacitor. As a result, the voltage across each capacitor will increase more slowly, and the voltage at the end of the 10-second time period will therefore be smaller. Therefore, as far as the external world is concerned, multiple capacitors connected in parallel behave just like a single capacitor with a larger capacitance. Here's another way to look at it. Multiple capacitors connected in parallel can be viewed as a single capacitor with a larger area. A capacitor with a larger area has a larger capacitance.
Let's look at a 2D circuit. So I have named the capacitors as 1, 2 and 3, and as we know, whichever is connected by a solid wire to the positive of the battery will have the same potential. So V1 is all lined up on the left hand side plates of these parallel plate capacitors. The right hand side plates of 1, 2 and 3 are all mentioned as having a potential V0 because all these three are connected by solid wires to the negative terminal of the battery. Therefore, the two plates of each of these capacitors is having a potential difference of V1 minus V0 across those two plates with the dielectric in between. So if we take the first capacitor, Q, the charge on the first capacitor is generally equal to CV. Therefore, Q1 will be equal to C1 into V1 minus V0. Since we put V0 equal to 0, therefore it will be C1 V1. This is how you start deriving. Now, if we come to the second capacitor, Q2 again will be equal to C2 into V1 minus V0. We put V0 as 0, therefore it is C2 into V1. So that's how we start deriving the charge distribution among these three capacitors in parallel. Coming to the third capacitor, Q3 again will be equal to C3 into the same potential difference, which is V1 in this case. So it's becoming simpler now. So we have fixed the charges that got distributed among those three parallel capacitors. So now we know that the battery gives a plus Q charge, which is written on top of that line, and a minus Q charge. So battery charge total is Q. So let's add up these individual charges. So Q1 plus Q2 plus Q3 must be equal to total charge supplied by the battery, which is Q. So C1 V1 plus C2 V1 plus C3 into V1 is equal to Q. So branch the C1 plus C2 plus C3 together, and therefore you will get the equation that you see there, and C1 plus C2 plus C3 will be equal to Q by V1. This leads us to the total equivalent capacitance of such a combination. So the equation very clearly is the C total is C1 plus C2 plus C3. The charge on that system in between those two bus bars will be Q equal to C total into V1. This is the charge supplied by the battery.